So imagine you're cruising at 35,000 feet over a conflict zone.
Right, in the middle of the night.
Exactly. It's a totally quiet night on the flight deck. And then suddenly, your terrain alarms just start screaming that the aircraft is about to fly head-on into a mountain.
Which is terrifying.
Right. And your autopilot aggressively banks the plane to the right to avoid it. But the catch is the aircraft is actually flying over perfectly flat desert terrain.
Yet there are literally no mountains around.
None at all. The plane's navigation computer has essentially just been hijacked by invisible radio waves.
It is a terrifying scenario.
Yeah.
And frankly, it's the absolute definition of, an operational minefield out there right now, which is exactly why we're bringing you onto the flight deck for this briefing.
Welcome aboard. You're joining two senior Airbus flight instructors for a deep dive into A320 navigation management. We've got a pretty sick stack of material to get through today.
We do. Recent Airbus safety bulletins, updates to the FCOMM, the Flight Crew Operating Manual, and a lot of our own internal simulator training reports.
Yeah, and our mission here is really to explore the precise criteria and the exact execution for, when a pilot actually has to manually cut off the aircraft's GPS and radio navigation signals.
Because managing degraded navigation is, well, it's no longer just a peripheral, once-in-a-while skill that instructors test crews on during a recurrent sim check.
Right. It's everyday life now.
Exactly. In today's airspace, particularly with the rise of electronic warfare kind of spilling over into commercial flight corridors,
Yeah.
it is a core fundamental requirement for operational safety.
I actually like to think of the Flight Management and Guidance Computer, the FMGC, as this highly trained, incredibly efficient assistant sitting between the pilots and the cockpit.
That's a good way to look at it.
Yeah, and this assistant is brilliant at executing complex math, right? But they rely completely, blindly on their reference materials.
Right. The system has no innate intuition. None at all.
Yeah.
It only knows what its sensors actually tell it.
So when those reference materials are corrupted, the flight crew has to step in. They have to actively curate exactly what this assistant is allowed to read just to ensure the aircraft keeps flying safely.
Totally.
But before we get into the actual mechanics of how a pilot cuts off the computer's information sources, we really need to establish how the system actually figures out where it is in the sky in the first place.
Yeah, because to protect the aircraft's position, you really have to understand how that position is built. And it all starts deep inside the avionics bay with the IRS.
The inertial reference system.
Exactly. The A320 has 3 of them, actually. And the flight computer is constantly calculating a mix IRS position, which is simply the mean weighted average of those 3 independent systems.
Okay, let's break that down mechanically for a second. How is an internal system sensing its position without, physically looking outside?
Well, it's pure physics. The IRS uses these laser ring gyroscopes and accelerometers.
Oh.
Yeah, it physically senses the aircraft's pitch, roll, yaw, and forward acceleration. So by mathematically calculating that physical movement over time, the aircraft basically senses its own path through space.
That sounds foolproof.
You'd think so, but there is a massive inherent flaw here. These physical systems naturally drift.
Drift? Why do they drift?
Because no mechanical or optical sensor is absolutely perfect. They're incredibly precise second to second, but over a 4-hour flight, tiny microscopic errors in measuring that acceleration start to accumulate.
Oh, I see.
Yeah, so without external correction, the raw IRS position will slowly wander, miles away from the aircraft's true geographic location.
So the IRS is essentially like a wind-up pocket watch that runs just slightly fast. Over 4 hours, it's going to be a few minutes off.
That is a phenomenal way to visualize it, yes.
And meanwhile, the GPS satellites are like the atomic clock on your smartphone.
No.
So to fix the drift, the flight computer calculates what is known as a bias vector.
Right, the bias vector.
And that bias is just the underlying math the system uses to calculate exactly how fast that pocket watch is ticking so it can constantly, correct the time in the background.
Exactly. The computer applies this computed bias vector to that drifting mix IRS position to generate the highly accurate FM position.
Okay, that makes sense.
And to calculate that bias, the system references external navigation sources based on a rigidly programmed hierarchy. Priority number 1, the absolute top of the food chain, is GPIRS.
Which is GPS combined with the IRS data.
Spot on.
Wait, so if the GPS fails or, the satellites are jammed, how can the plane possibly know where it is using just the ground radios? Is it triangulating signals like a cell phone tower?
It actually operates on a very similar principle. If GPS is lost, The system steps down to priority number 2, which is radio triangulation using DM and DM.
Distance measuring equipment.
Right. The aircraft measures the radio ping return time from 2 or more ground-based DME stations to lock in a geometric position.
And what if it can't find 2 stations?
Then it steps down to priority number 3, which is a single VOR DME. It basically uses bearing and distance from one co-located ground beacon.
Okay, but what if the aircraft is out over the middle of the ocean, where there are literally no ground radios and the GPS is out?
Then it's priority number 4, IRS only.
Oh, boy.
Yeah. The system enters inertial coasting. Because it's lost all external inputs, it simply applies the last memorized bias vector to the drifting mix IRS position.
Just hoping for the best.
Basically, it's hoping that whatever mathematical correction it was using, say, 5 minutes ago, is still relatively accurate right now.
Which raises an incredibly important and kind of scary question. If that inertial coasting mode relies on applying the last memorized bias to a drifting system,
Right.
what actually happens if that memorized was created while the GPS was actively feeding the aircraft lies?
And that is the million-dollar question.
What?
We will tackle the simulator traps involving a poisoned bias in a moment, because it is absolutely the most dangerous scenario a crew can face.
Yeah, we definitely need to get into that.
But to get there, we first need to look at the initial layer of data corruption that crews actively manage on a daily basis, which is terrestrial radio beacons.
Right, those terrestrial beacons. The VORs and DMEs representing priority 2 and 3. Because the flight computer relies so heavily on them when GPS is degraded, the crew really has to ensure those ground stations are actually broadcasting clean data.
They do. Because these are physical machines sitting out in fields or near airports or, on top of mountains. They are highly vulnerable to real-world issues.
Like what? Weather?
Sometimes. But also, a transmitter might just require routine maintenance, or it might suffer from signal multipath errors.
Multipath errors?
Yeah, that's where the radio wave bounces off a newly constructed skyscraper and confuses the aircraft receiver. Or the station might just be undergoing calibration testing.
And pilots find all these warnings buried in their pre-flight paperwork, right? The NOTAMs, or notices to air missions.
It's exactly. A crew might review a massive stack of briefing papers in the departure lounge, and on page 12, it simply states that the BPK ground beacon is unserviceable.
So if the flight crew knows a beacon is bad from the NOTAMs, but they don't, manually tell the computer to ignore it, what happens?
The system's auto-tuning logic will just go ahead and use it.
Wow.
Yeah. The computer will reach out, grab that unserviceable signal, and actively degrade its own navigational accuracy because it's pulling garbage data into its position calculations.
It honestly sounds a lot like using a car's GPS. If you know a specific highway route is closed for construction,
Right.
but you don't explicitly go into the settings and tell your app to block that road, the automated routing logic is just going to continually try to pull you back into the construction zone.
Constantly recalculating and destroying your ETA.
Exactly. You have to manually restrict it.
Right. And in the A320, crews build that fence using the MCDU, the multifunction control and display unit.
Which is essentially that primary computer keyboard sitting right between the pilots.
That's the one. FCOM standards dictate a very specific flow to lock out a bad ground station. The pilot selects the data key in the MCDU keyboard, presses the position monitor prompt on the screen, and then hits Cell Evades.
Which brings up the page where the crew can curate exactly what terrestrial signals the aircraft is allowed to listen to.
Exactly. So to inhibit a specific station, the pilot types the 3-letter identifier like BPK into the scratch pad at the bottom of the screen and then inserts it into the deselect field.
And boom, blocked.
Yes. The flight computer is now procedurally blocked from using BPK. Alternatively, if a crew is in a severely degraded environment and wants to wipe the slate clean, they can press the deselect all radio navates prompt to just shut out all ground stations entirely.
Okay, so that handles the terrestrial threat. But ground beacons usually fail due to benign maintenance issues. GPS faces a much more insidious threat, and it requires a completely different operational response.
Oh, absolutely.
We're talking about intentional GNSS radio frequency interference.
We are talking about malicious interference, primarily military-grade electronic warfare. And it basically presents itself to the aircraft in 2 distinct ways: jamming and spoofing.
Right. Let's start with jamming, which is essentially signal loss. Someone on the ground points a massive transmitter at the sky and blasts high-power radio noise on the GPS frequencies.
Because, the actual GPS satellites transmit at a very low wattage from 12,000 miles out in space. It is an incredibly faint signal by the time it reaches the aircraft receiver.
Like a whisper?
Exactly. So a jammer on the ground simply overwhelms that faint signal with raw power.
Yeah.
The GPS receivers on the aircraft get flooded with noise and just go completely blind.
But the aircraft software is highly aware that this is happening, right? Triggering a GPS primary loss message on the central alerting screens.
Yes.
I sort of look at jamming, like the aircraft temporarily going deaf. It suddenly realizes, hey, I can't hear the satellites anymore. So it instantly switches to using its backup senses, its radio ears, and its internal inertial balance.
That's a perfect analogy. It is a recognized system failure. And this is a vital operational point. When an aircraft is jammed, the flight crew does not need to manually deselect the GPS.
Really, no manual action.
No manual action. The A320 architecture is robustly designed to handle signal loss. The system automatically steps down that hierarchy we outlined earlier, reverting to radio updating or IRS coasting. The pilots won't even experience a sudden map shift. The transition is seamless.
Okay, but spoofing. Spoofing is not deafening the aircraft. Spoofing is someone whispering false directions into its ear.
It is a deliberate deception attack. The attacker broadcasts a highly structured, fake GPS signal that is just slightly stronger than the real satellite broadcast.
And the plane just buys it.
Totally. The aircraft's receiver locks onto this fake signal, and the flight computer does not know it's being lied to. It genuinely believes it has perfect Priority 1 GPRS data.
If spoofing is such a massive known threat in modern aviation, why doesn't Airbus or, the avionics manufacturers simply program the computer to recognize when the GPS is lying?
That's what everyone asks.
Why does the burden fall to a stressed-out human pilot to catch the lie and hit a deselect button?
Honestly, it's a limitation of current software versus incredibly sophisticated electronic warfare. The spoofing signals are perfectly formatted mathematical data packets. They mimic satellite trajectories and timing signals flawlessly.
Oh, so the math checks out.
The math checks out perfectly. Because it trusts that top-tier data implicitly, it starts updating its geographic reality based entirely on the attacker's fake coordinates.
Which leads to absolute operational chaos on the flight deck. You get map shifts where the aircraft's position on the navigation screen suddenly jumps sideways by 50 miles.
Yeah, you get terrifying terrain warnings.
And most dangerously, if the autopilot is engaged in NAV mode, trying to follow its programmed route, it's going to execute sudden, uncommanded turns as it attempts to steer the plane toward the spoofed trajectory.
Exactly. And because the computer software doesn't recognize the deception, the automatic reversion that saves you during a jamming attack simply does not happen.
So you have to intervene.
Manual intervention by the pilot is the absolute only way to sever the connection. The crew must navigate the MCDU to the correct page and physically press the Deselect GPS button.
Putting up a firewall.
Yes. By doing that, they create a manual procedural firewall, forcing the computer to ignore all satellite data and stopping the poisoned information from feeding the autopilot.
But, understanding the theory of a spoofing attack is one thing. Recognizing it and actually executing the deselection under pressure in the real world is entirely different.
Which brings us to the simulator traps.
Right. Instructors see highly experienced crews fall into specific, predictable errors when dealing with a spoofed system. Let's unpack trap number 1, the poison bias. This goes right back to my question about coasting on bad math.
It does. Consider a scenario where a crew flies into a spoofed airspace. The false GPS data slowly pulls the aircraft's internal position away from reality. So the flight computer is actively recalculating its bias vector, that mathematical correction we discussed, based entirely on this fraudulent data. After a few minutes, the pilots notice their map has shifted. They realize they're being spoofed, and they correctly hit Deselect GPS.
Most pilots would assume the threat is neutralized at that point, right?
They would.
Yeah.
But if they deselect the GPS after the spoofing has already taken hold, the flight computer drops down into IRS coasting mode, but it permanently freezes the last calculated bias vector.
Oh, man. So it memorizes the corrupted math?
It memorizes it. The map shift will persist even with the GPS totally shut off because the inertial system is still actively applying that poisoned mathematical correction in the background.
It requires such a deep understanding of the system's underlying logic to know how to fix that. The pilot has cut off the bad data feed, but the damage to the internal math is already done. So how do they flush it out?
The crew has to perform a manual position update on the pirogue page, the progress screen on the flight computer. But they can only execute this when they are physically flying directly overhead a known verified radio fix, like a VOR beacon.
Right, so you visually or physically confirm you are over the station.
Exactly. The moment they pass over the physical station, the pilot forces the flight computer to update its geographic coordinates to that exact point, which basically flushes the bad math and recalculates a clean, true bias.
That is wild. Okay, trap number 2 is incredibly dangerous because it preys on fundamental pilot psychology, the EGPWS panic.
Ah, yes. The Enhanced Ground Proximity Warning System. This is the ultimate safety net for preventing controlled flight into terrain.
But it relies on GPS, doesn't it?
It relies heavily on GPS data for its look-ahead terrain awareness display and its predictive terrain clearance floor. It basically compares the aircraft's GPS position and altitude to a global topographic database.
But in a spoofing environment, the attacker's fake GPS signal might suddenly report a false altitude or location. Suddenly, the EGPWS thinks the aircraft is 100 feet off the ground in the middle of a mountain range.
And it triggers a spurious, blaring pull UP warning in the cockpit.
I mean, I hear you. But telling a pilot to ignore or manipulate a screaming terrain warning system in a panic scenario sounds incredibly counterintuitive. Are crews really comfortable doing that?
It's extremely hard.
Why?
Human instinct is to silence the alarm. We see crews in the simulator get so overwhelmed by the sheer volume of the false warnings that they reach up to the overhead panel and switch off the entire GPWS system just to make the noise stop.
Just shutting the whole thing down.
Yes, and instructors must fiercely train crews never to do that. If you turn off the master system, you strip away every single layer of terrain protection.
So what is the Airbus procedure to handle a false terrain warning caused by spoofing?
The pilot must go to the center console and push the specific turbo push button to the off-F position.
Just the terror button.
Yes, just that one. This isolates the system. It inhibits the predictive look-ahead database, which is what the spoof GPS is confusing, and it will trigger a caution message on the ECAM, the central alerting screen. But crucially, it keeps the basic, foundational modes of the ground proximity system fully operative.
Because those basic modes rely on the radio altimeter looking straight down at the ground, and the barometric altitude, they don't rely on GPS.
Precise.
So the aircraft still has a functional safety net if it actually gets too close to the ground, while ignoring the false look-ahead data.
It's all about surgical intervention. You isolate the compromised subsystem without disabling the core safety features.
Man, that's smart. Let's move to trap number 3, which is incredibly subtle and catches crews before they even leave the runway. The takeoff update.
Ooh, this is a tricky one. Imagine an A320 departing from an airport in a region where GPS spoofing is rampant. Because of the interference on the ground, the aircraft's initial IRS alignment at the departure gate might be degraded, meaning its starting internal position is already slightly off.
Normally, the flight computer has a built-in mechanism to fix any taxi drift, right? Like when the pilot lines up on the runway and pushes the thrust levers forward to TOGA or FLX, which is essentially flooring the gas pedal for takeoff power, the flight computer automatically snaps its internal position to the precise, published coordinates of the runway threshold.
Exactly. That automatic runway update zeroes out any internal errors before the aircraft even takes to the sky.
Okay.
However, that vital automatic update is hard-coded to be inhibited if the flight computer registers that GPS primary is active.
Wait, why?
Because the system logic dictates that if it has a perfect GPS signal, it doesn't need to manually update its position to the runway coordinates. It thinks it already knows perfectly well where it is.
Oh, I see. So if a crew is being spooked on the taxiway and the flight computer falsely believes it has GPS primary, it skips the takeoff update entirely.
You got it. The aircraft will launch into the air with a degraded inertial position combined with a spoofed GPS position. It basically guarantees a severe navigation failure the moment the aircraft rotates off the runway.
That's a huge trap.
So to prevent this, if a crew suspects spoofing on the ground, they must proactively navigate to the MCDU and manually deselect the GPS prior to beginning the takeoff roll.
Yeah, force it off.
Forcing GPS off ensures the computer actually executes that vital runway position update when takeoff thrust is applied.
You know, in all 3 of these simulator scenarios, the poison bias, the terrain warning panic, and the takeoff update, the true danger isn't the aircraft failing mechanically. The danger is the human pilot fundamentally misunderstanding the automation's logic.
Absolutely. The machine operates exactly as it was programmed. It is the flight crew's ultimate responsibility to understand why the software is acting a certain way and how to assert control over it.
So we have established how easily a pilot can be tricked in the simulator. But outside the sim, in the real world, how does Airbus actually expect crews to manage this degraded state? I assume that's where the core airmanship rules come into play.
Exactly. Airbus publishes golden rules for pilots, and managing navigation threats ties directly into golden rule number 2. Use the appropriate level of automation at all times.
And golden rule number 1? Fly, navigate, and communicate.
Yes.
Let's outline the immediate real-world actions. A crew is in cruise, they observe a sudden map shift on their screens, and the autopilot begins an uncommanded turn. What is the very first physical action the pilot flying must take?
The pilot immediately disconnects NAV mode and pulls the heading or track knob. They take physical lateral control of the aircraft away from the flight computer.
Downgrading the automation.
Exactly. The fundamental rule is never to blindly follow a magenta route line that cannot be independently verified. You downgrade the automation.
Stop the aircraft from turning on its own. First, fly the plane.
Right. Once the flight path is stabilized, the crew must determine the actual severity of their navigation degradation by executing a navigation accuracy check on the pierogi page.
How does a pilot manually verify the computer's accuracy against raw data?
The pilot enters a known physical VOR or DME ground station into the bearing and distance field on the computer screen.
Okay.
The FMGC will then calculate what it estimates the bearing and distance to that ground station should be, based purely on its internal position math.
Got it.
The pilot then looks at the navigation display screen and checks the raw, physical radio needles pointing at that exact same station.
So they're basically comparing the computer's generated guess against the actual physical radio waves hitting the aircraft antennas.
Precisely. If the computed distance and the raw radio distance agree, the flight computer's position is verified and accurate.
Yeah.
But if they disagree, if the computer calculates the station is 20 miles away, but the physical radio signal proves it is 40 miles away, the computer is officially lost.
And SCOM procedures dictate that if the check fails, the crew must entirely revert to selected guidance and raw data navigation.
They do.
They tune the physical radios, follow the raw needles, and essentially fly the A320 exactly like an analog aircraft in the 1970s.
Yeah.
Because the ultimate safety firewall on a multi-million-dollar commercial jet isn't the satellite receivers or the complex algorithms, it is a human pilot's situational awareness.
Automation is a highly effective tool, but it makes a terrible master. Managing an A320's navigation in modern airspace requires the crew to actively guard the inputs feeding the flight computer.
You really have to protect it.
You must understand when the system is allowed to use GPS or radio-Nav aids, and you must know the exact procedural execution to cut those sources off to protect the integrity of the aircraft's position.
That perfectly summarizes the mission for this briefing. Whether it's understanding the physics of inertial drift, building an electronic fence around a bad ground beacon, or putting up a procedural firewall against a military spoofing attack, it all comes down to controlling the reality your flight computer is permitted to perceive.
The operational landscape is evolving rapidly, and a pilot system's knowledge has to evolve right alongside it to ensure passenger safety.
We started this deep dive by examining the flight computer as a brilliant assistant who blindly trusts its references, and we've explored just how vital it is for the pilot to curate those inputs. But before we wrap up today's briefing, I want to leave you with a final provocative thought. As GNSS spoofing becomes increasingly sophisticated and widespread, turning the invisible radio frequencies around commercial flight corridors into an active electronic battlefield, how long will it be before commercial aviation must pivot away from RF-based updates entirely and develop a fundamentally new, unhackable positioning hierarchy? Something to think about next time you were cruising at 35,000 feet. Until then, keep flying the plane and never trust the magenta line unless you can prove it.